Okay, so welcome back to the fourth lecture on gravitational waves. So today we'll be talking about cosmological sources, and that's where we make the connection to BSM physics, because nearly all the sources that I'll be talking about will be some form of BSM. To recap briefly from last time, right? So by now you recognize the wave equation for gravitational waves. There was a question after the lecture that I couldn't answer, so let me answer it now. And this was when we went to the H tilde variable, right? So to this guy, this first derivative somehow magically turned into something like a double prime h bar, right? And the way that magic happens is just when you insert that into the box operator, right? From the time derivative, you get one term a prime h prime, which just cancels this, and the other surviving term is the one that we had on the board, so the a double prime h term. So that's how that magic happened. But okay, that was just a side remark. Then we discussed at length the energy density in gravitational waves, and that will become important again today, right? So we derived that we can get it from the average over the first derivative of the two-point function of the gravitational wave. And we also saw that it takes this kind of, it factorizes into this type of expression where we have an integral over k, and then we have the primordial component, which characterizes the power spectrum of the gravitational waves at the time of emission, and then the transfer function, which describes how this power spectrum is redshifted throughout the universe. And for convenience, often we basically take the integrand here and call it omega GW. And then we also talked a bit about detectors. We had a lot of very complicated expressions on the board, but I think that the thing you want to remember is that if you look at the signal you observe in the detector, right, be it just the linear response, or be it here, as I'm writing here, the two-point function, you always get something which is of the type that you have the detector response multiplying the primordial signal or the primordial power spectrum with some integral over all directions, the entire sky, and a sum over polarizations. And then if your situation is simple, you may be able to take either this or parts of this and take it outside of these sum or these integrals. But that is kind of the generic structure that you should always expect from a gravitational wave instrument. Okay, so today we want to talk about cosmological sources. And before we go to concrete models, let me say a couple of more general words. And the first point is about the characteristic frequencies that we expect. So the question is, okay, you have some source, right? Doesn't matter what it is. You can think about a phase transition in the early universe, or also something violent, something that has a large quadrupole moment, something that is time dependent, something emitting gravitational waves. How can I do a back of the envelope estimate to see at which frequency should I build a detector to look for this particular source? So say we want to observe, or say we have a gravitational wave emitted at some frequency f star, right? Then we need to take into account the redshift, right? So we will observe this gravitational wave at the emitted frequency times the redshift. Okay, so now I'm just writing a star instead of a of tau star, just for notation. And then I need to know, okay, well, how does my emitted frequency relate to my cosmological event? And I can just parameterize the frequency as corresponding to some typical length scale in units of the Hubble radius at that time. So typically for cosmological sources, the Hubble scale is the relevant length scale, right? So this epsilon will be roughly 1. You can also have sources which are smaller than the Hubble scale at that time, right? Because you have some other mass scale in the problem which is driving it. Then epsilon can be a bit smaller. For any causal source, epsilon can never be bigger than 1. Okay? So the only way you can have epsilon bigger than 1 is you can try doing something funky during inflation, right? But remember that everything super horizon is frozen anyway, right? So really, even if you have inflation, the relevant scale when the things are oscillating is still the Hubble scale. So again, epsilon star will be about 1. So typically, epsilon star is roughly 1, can also be a bit smaller. Okay, but now we just need to plug this into our standard model of cosmology. For simplicity, we'll just consider the radiation era, because that is, after all, most of our cosmic history. So we can use that the Hubble parameter is just given by some prefactor temperature to the 4, right? Where again, the star is indicating, okay, at some given point in time, in this case here, the time where this is emitted. And now I can just plug everything inside, right? I know how time scales with temperature. I know how A scales with temperature. So I can just use these relations. And I will obtain, just to give you a benchmark, that say we have an event happening at a temperature of a GeV. That will be observable today at a frequency of 10 to the minus 8 epsilon star to the minus 1 hertz. Or we can also put that into a time, right? We can say that this implies, I don't know, let's take a frequency we observe today of 1 hertz, right? So something close to LIGO. This corresponds to a time in the evolution of a universe of 10 to the minus 22 seconds. And you will see here that the higher the frequency, the more you are going to events in the early universe. If we look at where typical experiments are sensitive, right? So say we have pulsar timing arrays. They are sensitive at about 10 to the minus 8 hertz, right? So this is precisely this benchmark points here, right? So they are a priori roughly probing the GeV regime. Right, T star here in GeV, right? Roughly 1. Lisa, right, is roughly sensitive at 10 to minus 2 hertz. So that gives you, if you take epsilon to 1, right, that gives you a sensitivity of 10 to the 5 GeV. When we talk about phase transitions, this epsilon here is a bit smaller than 1. It's typically 10 to minus 2, 10 to minus 3. And that's where that statement comes from, that Lisa is sensitive to the electroweak phase transition, about 100 GeV. Right? That's just because here in this little table I've set epsilon star to 1, right? But you should keep in mind that making epsilon star smaller brings these scales down a bit. And then finally, LIGO, the 100 hertz, this roughly corresponds to a temperature of 10 to the 9 GeV. So you see that in principle, right, these, I mean, in particular here, these are, and LIGO in particular, right, I mean, these are scales way beyond anything we're going to reach at a collider in any foreseeable future, right? So in principle, the idea is that if you have an event in the early universe and you have detectors at these frequencies, in principle, you can probe up to very early times in the evolution of our universe, and you can probe particle physics up to extremely high energy scales. Now, the problem, of course, is what we also saw the other day, right? That when we solve this equation of motion, we get the 1/a decay factor inside the horizon. So events which are produced particularly early also had a lot of time to evolve in the universe, and hence their amplitude was suppressed. So even if initially the amplitude was maybe large, over time the amplitude decreased. So it's very difficult to actually get the sensitivity to probe cosmological events, right? So there's always two factors to it. One is, do I get the right frequency? And the other one is, do I get the right amplitude? Do I get the right sensitivity of my detector? But this is a bit the motivation why people say that gravitational wave detectors could really be a way to probe particle physics far beyond the reach of any other instrument that we can imagine. Okay, do we already have, okay, so here we've talked about frequency, right? Now let's talk about amplitude. Okay, I'm not very organized on my blackboards today. So epsilon star is the typical scale of whatever your source in units of the Hubble horizon at that time. Okay, so typically for cosmological sources, the Hubble scale is what sets the scale of the source of the dynamics. So if you think topological defects, inflation, their epsilon star would just be 1. But then if I think phase transition, and then I also have a kind of the size of the bubble, right? And the size of the bubble can be smaller than the size of the horizon, right? But I can compute by, it will still scale with the size of the horizon, which is why this is a useful parameterization. And typically things are not much smaller than few orders of magnitude smaller than the size of the horizon. We'll get there. We'll get there. But basically, what you would need to do, you would need to compute, okay, the size of the bubble and the bubble-bubble separation, right? Those are the relevant scales. So in a given model, you would need to compute them and see how that relates to the size of the horizon at that time. It is model dependent, yes, totally, yes, yes. Okay, so let's talk about the amplitude. And for the amplitude, we actually already have a constraint, not only from the direct observations that we have, say, with LIGO, but also from cosmology. So we have a constraint on the amplitude from BBN and CMB. And then there's a constraint on the total amount of radiation in the universe, okay? Because gravitational waves are massless radiation, so they act like extra photons, extra neutrinos in our universe, and they are hence constrained by the amount of radiation that we are allowed to have in our universe. So extra radiation. Right, so after, if we go to some point in the universe after the electron decoupling, then the radiation density that we have in the universe, we can compute in the standard model, pi squared over 30, 2, this is the photons. Now, I add the neutrino term. Okay, so radiation energy density scales with T to the 4. The 2 is the 2 degrees of freedom of the photon. Here come the neutrinos. Here you have a prefactor just because they're fermions. This 4 over 11 is the difference of the neutrino temperature to the photon temperature, because when the electrons decay, they reheat the photons, but not the neutrinos. And the n here is the number of neutrinos. So in the standard model, right, this is 3.046. It's not exactly 3, and that has something to do with the fact that the neutrino decoupling and the reheating of the photon plasma are kind of close together. So there are some corrections to that. But this is the status in the standard model. And now people often define the delta N effective as the additional, basically comparing this to observation and asking, okay, how much more radiation is allowed by observations, or what is the limit on extra radiation by observations? So since gravitational waves are radiation, right, so the amount of energy in gravitational waves normalized to what we have in photons, right, has to be smaller than whatever we observe in radiation minus what we know we have from the standard model. And this is exactly what is parameterized by N effective. So the delta N effective bound that we can get from the CMB and from BBN, basically bounds on expansion history, are directly bounds on the total amount of energy we can have in gravitational waves. And this rho here, of course, is nothing else than the thing we were computing yesterday, right? It's the total amount of energy that we have in gravitational waves. So now we know that at and after BBN and CMB decoupling, we know from measurements that this thing has to be smaller than about 0.2, which means that the total amount of energy relative to the amount of photons has to be about less than 10% at the time of BBN and CMB decoupling, right? Which is a lot, right? Because here we're in radiation-dominated era, right? So the rho photon is basically the entire energy density of the universe at that time. And we're saying the bound that we have just means that we can't have more energy in gravitational waves than 10% of the total energy at that time. And it makes sense that that's all we can get, right? Because we're putting bounds on expansion from the expansion history of the universe, right? We're only going to kind of see changes in expansion history if this is a significant contribution. Okay, but then we want to look at this today. And so if you look at this today, right, so we want to put a bound on rho gravitational wave today, then we have to take into account that both the gravitational waves and the photons redshift until today. So this 10% will translate to say that the energy density in gravitational waves today is this 10% times the fraction that we have today in photons times the total energy density. But this thing is only about 10 to minus 5. Okay, so this is the statement that photons redshift faster than matter, and hence today we only have a small fraction of photons compared to matter. So that means that today the fraction of energy we can have in gravitational waves cannot be more than about 10 to minus 6. Okay, note that this is a bound on the total energy density. This is not a priori a bound on the spectrum or the amplitude of the spectrum. However, oftentimes people will use it as a bound on the amplitude, and that is okay under certain assumptions, right? So often when people write, instead of this bound, they say omega gravitational waves, so the spectrum should be smaller than 10 to minus 6. And that is okay under the assumption of a broad spectrum, which is, for cosmology, kind of okay. So what you're doing here is you're saying, okay, I have a total bound on the energy density. Now I'm going to expect my spectrum, to be kind of in log space, kind of wide, right? So I kind of expect, that here if this is LNF, right, then these are kind of the width of the spectrum is some order unity in log space, which is for cosmology kind of what I expect, because things only ever evolve on the time scale of e-folds, right? So things in cosmology only ever evolve on a logarithmic scale. So if I have a spectrum like that, then I can say, well, this is actually a bound on the integrated spectrum, but well, I mean, roughly this is a square, right? And if this is roughly a square, right, then I can turn the bound on the integral into a bound on the integrand, and this is where this bound comes from. So I'm stressing this because when you see this bound, you'll see this a lot. This is fine most of the times, right? But there's some cases where it's not fine. And the cases that it's not fine is either when your gravitational wave source was only active after BBN and CMB, right? Because then this derivation doesn't hold anymore, because then you wouldn't, BBN and CMB wouldn't be sensitive. And the other point it doesn't hold is if you have some super spiky spectrum, right? Some sharp peak, then you actually have to go back and you have to calculate the integral, and then you can put the bound. Okay, any questions on this? Okay, so now let's get to cosmological sources. Okay, so recall from last time, right? That equation up there, the first equation on the first board. If we go to this H tilde basis, right? It looked like this with H tilde Hj double prime k of tau plus k squared minus a double prime a H tilde Ij k of tau is 16 pi G A pi Ij k and tau, right? And this H tilde was A times H. So now we can, okay, now we want to, okay, so I'm using spatial indices only, again, because at the end of the time, I mean, in the source, of course, I cannot use TT gauge, but at the end of the day, I will be interested in my gravitational waves far away from the source, right? So at the end of the day, I will anyway use TT gauge. But for now, this is the general, just I've restricted myself to these indices. And we can write down the formal solution to this equation, right? Yesterday, we were setting the right-hand side to 0 and just looking at the propagation. Now we want to discuss the sources, right? So we have to keep the right-hand side. So then it's more difficult to solve this equation. But at least formally, we can write down that this thing, Hij of k and tau, is the right-hand side, 16 pj over a. And then we're going to use Green's functions method to solve this. So I'm integrating from some initial time to the time I'm interested in over d tau prime, the Green's function of the matching the differential operator on the left-hand side of this equation. Depends on k, depends on tau, depends on tau prime. And then the source term, pi aj of k and tau prime. Okay, so this is the formal solution, right? The Green's function has the property that this differential operator acting on the Green's function gives a delta function, right? So then if I put correctly the factors of a, right, you see that this will match the equation. This 1 over a comes from, right, the fact that here I'm using h tilde and here I'm putting back h, right? So I just did the 1 over a at the end. So this is formally a solution. The Green's function to this differential operator is not a secret, right? So this is given by sinus k tau minus tau prime divided by k. Okay, so if you know what is the energy momentum tensor of your source, you can, in principle, perform this integral, at least numerically, and you know what is the gravitational wave observed at whatever time you're interested in. This is the Green's function, I should say, for k larger AH. Okay, so this is the Green's function in the sub-horizon limit, which is what we would be interested in everything that we're doing today. Questions? Okay, so now we can take this expression and put it back into the expression up here for the energy density. Okay, and so because the goal is, what we want to know, for any cosmological source, the prediction will be some spectra omega of f, right? Because that's the thing we can measure, right? That's the thing that shows up in the response function of the detector. So we want the energy density, and even better, we want directly this omega, right? So we want d omega gravitational waves of d ln k. We use this expression up here, right? So we need to take this guy, we need to take the time derivative, and then we need to form the two-point function, and we need to add the prefactors that we have up there. So this gives 2g over pi k cubed a to the 4. Now we have two time integrals over d tau 1, d tau 2 from the two parts of the two-point function. We have the scale factor, a of tau 1, a of tau 2. We have the cosine, because we've taken a derivative. And then we have what is called the unequal time correlator. So let me just give it a name, k tau 1, tau 2. But what is this thing? It really just comes from combining two of these factors. So it's the expectation value of, or the average of pi aj k tau contracted with pi aj k prime tau prime. And this will give you 2 pi cubed delta function using, again, isotropy. And then this object here. Okay, so this object here is basically the power spectrum, if you want the power spectrum of the anisotropic part of the energy momentum tensor. Okay, it's just a name, but if you know the source, right, so you've simulated the phase transition on a computer, right, you know the energy momentum tensor, you can compute this power spectrum, right, and that is the source term, which then enters here on the right-hand side. You need to do two time integrations, and then you get the energy density. So this is, in principle, how you proceed, right? So now in principle, you can take any arbitrarily complicated source that you have in your model, right? Assuming you can solve your model, assuming you can solve for the energy momentum tensor, this is kind of the instructions on how, at least in a formal manner, you solve and you get the omega, you get the power spectrum of the energy density. Now, in practice, oftentimes you can make your life much easier, right? And you can avoid doing all these integrals because you can do some physics arguments and make your life easier than what we're doing here. But I wanted to show you once, if you don't have a clever way of doing it, then you can always resort, in principle at least, to this way of doing it. Now, in the following, we'll be talking about two types of sources. Fundamentally, there are two types of sources. One are transient sources. And here, when I say transient, I don't mean like in LIGO, right? There's also transient, right? So LIGO is really, it's transit in your detector, right? So you see it's gone. Here, all cosmological sources are always in your detector, right? The cosmological source, you cannot turn it off, right? You cannot wait and it goes away. It's always in your detector. So from point of view of the detector, they're not transient. But when I say transient here, I mean that in cosmic history they are transient, right? So it's some event that happened and then it was over, like CMB decoupling, like a phase transition. Whereas we can have other sources which continue over a very long time period in cosmic history, right? So transient cosmos sources. And what I mean here is basically that the duration of this source is not much longer than an E-fold, right? Not much longer than a Hubble time. Right, so some specific event in cosmic history, right? The duration should be less or equal to a Hubble time. And that means if the duration is short, right? I mean, recall that these here, I'm doing integrals over the source component, okay? So if my source component is only active for a short time, I only have to perform the integral over that short time. I don't have to perform the integral all the way to today, right? Because the integrand is 0. So if my source is short enough, then basically I can put a delta function here, and the integrals just collapse, right? And if I want to be more careful, I might want to do the integrals, but I don't have to do them all the way to today. I just have to do them over whatever time period the source is active. And consequently, you typically get some sort of peaked spectrum. And this relates to the discussion we had up here, right? Let me just put an arrow, where we can just estimate the frequency by the typical scale of the source, right? So basically, here we add a delta function in time, which is the point in time where the source is active. At that point in time, we can look at the energy momentum tensor, right? We will find there's a typical scale that describes the variations of the energy momentum tensor at that point in time. And then that scale just redshifts according to the arguments above. And so performing this integral will exactly recover the estimates that we did here. And then if we're just interested in the frequency, no need to do the integral because we already know the answer. The other situation that we can have is a continuous source. So an example that you've seen is inflation, right? So inflation, constantly you have modes re-entering the horizon, right? And these modes start to oscillate, and they contribute to your gravitational wave spectrum. So there's not one given point in time that I can say, aha, this is the point in time, I don't know, at 10 to the 10 GeV, where my inflation modes entered the horizon. No, right? I mean, all the time a different mode is coming into the horizon. So here, I will actually have to do the integration all the way from the onset, from the end of inflation all the way to today. I have to integrate over the entire cosmic history. And consequently, I cannot say, well, okay, there's one particular scale that should somehow be reflected in a peak in the spectrum, but rather I will be continuously getting gravitational waves, and I will kind of be building up a spectrum frequency by frequency by frequency. Right? The longer I wait, then I get different frequencies, and I start building up a very broad spectrum. And the perfect example of this is inflation, which we saw the other day, where you actually get a scale invariant spectrum over many, many, many orders of magnitude. So, for example, inflation. Another example, which we'll see in the second half of today's lecture, is cosmic strings. It's also a source that can be active over decades and decades and decades in cosmic history. And here we expect an extended spectrum, right? And to get the answer, we in principle do need to, if it's very simple, right? If it's scale invariant like inflation, right? We were able to estimate the spectrum just the way we did it yesterday or 2 days ago. If it's more complicated, you will have to go back to this integral, right? So if you recall it for inflation, there was two things that enters, right? One was the primordial power spectrum, that will basically, okay, so this is, I actually don't want to apply this to inflation, right? Because okay, so because in inflation you don't really have the source, right? You have 0 here, but instead you have an initial condition, right? So let's not apply this to inflation. But if I want to apply this to cosmic strings, I will get here something that parameters my initial source. And then on top of that, it will also depend on my entire cosmic evolution. And that's very similar to what we saw during inflation, right? It depended on the primordial power spectrum, and it depended on the cosmological evolution because there were some scale factors showing up. Okay, are there any questions? That's how much I wanted to say about kind of the general topic of cosmological sources. And then we can go into more concrete examples. But are there any questions so far? There's always more questions in the morning than in the afternoon. I wonder why is that? Actually, I probably wanted to. Okay, so let's start with the transient sources. And now we'll go through a couple of sources. I'll be very hand wavy, okay, because I only want to give you kind of the rough idea of the physics that's going on. I'm pretty sure that for nearly every one of these sources, there's probably somebody in this audience who actually knows more about it than I do. And also for every one of these sources, there's kind of a ton of papers, and very often also an ongoing debate of what exactly is the expected spectrum, right? So I'll mention some of the open questions to my best of my knowledge, right? But this is very much still a subject of research. Okay, so the first one is actually the only standard model source that I will be mentioning. And because it's standard model, it's going to be basically impossible to detect, right? And then we go to BSM and more optimistic perspectives. So this is the cosmic gravitational wave microwave, cosmic gravitational microwave background. Cosmic gravitational microwave background. Okay, so it is the CMB. It's a CMB with an extra G inside. But the logic is, it's called like this because it's supposed to remind us of the CMB. And the idea is very simple, right? So the idea is, okay, you have some primordial plasma. This emits photons. And this is the CMB, okay? And what sets the physics of the CMB? The physics of the CMB is set by the decoupling temperature of the photons, which is the recombination, right? When we electrons and protons combine into hydrogen, and that's about an EV. We can also imagine a process, right, where primordial plasma emits gravitational waves or gravitons. This will give the CGMB. But now, this decouples, right, in the sense that gravitational waves or gravitons drop out of thermal equilibrium at T is m Planck. Okay, now, however, our universe was never at a temperature of T equal m Planck. okay? Oh, these students who are chatting all the time, impossible. So, we expect, similar to CMB, right? We expect that, yes, this primordial plasma, will produce a bunch of gravitational waves, right? The spectrum will reflect, whatever temperature spectrum the CMB had, but its temperature will be significant, or its amplitude will be significantly suppressed because we were never in thermal equilibrium, right? So any production process will always be suppressed by some power of T over m Planck. So roughly what we expect, without doing any computation, is that this omega gravitational wave will have some suppression with some power of T over m Planck. And then it will follow the spectrum that we know and have measured from the CMB. Which is sad, right? Because this thing peaks, we know, at 100 gigahertz, roughly. We don't have a detector at 100 gigahertz, right? The highest frequency we can reach at the moment is LIGO. LIGO is 100 kilohertz. No, 100 hertz, right? So this is simply in a frequency regime that we currently don't have a detector to go at. And then also this is sad, right? Because, okay, we have a bound on the largest temperature that we can expect in the universe from the bound that we have on the highest scale that we could have for inflation, which is coming from the tensor to scalar ratio, right? So the observation of the, or the non-observation of the tensor to scalar ratio in the CMB tells us that there's an upper bound on the scale of inflation. That translates to an upper bound on the reheating temperature, which is about 10 to the 16 GeV, right? So this is smaller than 10 to minus 2, but could be arbitrarily small, right? Because we really don't know what is this quantity. So this is nice because it's a standard model source. However, both in frequency and amplitude, this is completely out of reach for the moment. It is, however, by construction, we can also already say that for sure this constraint that we derived from the VBN, right, will not affect this, right? Because basically this thing is the thing that saturates more or less the CMB bound by construction, and this is an additional suppression factor. Okay, so we conclude, as I said, this was the only standard model source I had, right? So we conclude that the standard model sources don't, like if you just have the simplest lambda CDM model, so you have single field slow inflation, right? We already saw, well, this leads to tiny amplitude. And we have this cosmic gravitational wave micro background, but again, the amplitude is too small. So if you just have lambda CDM with single field slow inflation, the most boring kind of complete model of the universe that you can imagine, you're not going to see cosmological gravitational waves anytime soon. It's the same as the CMB, it's a black body spectrum. So by the time you reach LIGO, it's ridiculously tiny. But that said, I think it's a motivation to build a detector here. Because you could measure the reheating temperature if you got down there.
But you would have high frequency way detectors you were proposing cannot reach such.
No, not you can get to those frequencies, but you cannot get to the sensitivity. Okay, so not even close. No way. At the moment, no way, right? No way, but if somebody has a good idea, right, how to build a really good detector at those frequencies, right, here's a source. A really interesting source.
Why is it
linear? A priori from the argument that I made here, right, this could be also some n, right, with n larger 1, right? If you do the actual computation, and people do it with kind of graviton emission, you find that it's linear. I don't have a good intuitive argument, right? But I think it can be linear at best, right? It only gets worse if it's higher powers. So okay, since you have your laptop, you can look it up. There's a paper by Andreas Ringwald, Jan Schütte-Engel, and they have the expression. So you can check if it's a typo in my notes, right? Or if we can think about what is the correct power. It has to be definitely at least linear, right? You're at least going to get one power of suppression. Okay, the second, we could also take a break. Let me think. Yeah, let's take a quick break. Let's take a 10 minutes break. Unless there's any more questions. Okay, and then we resume afterwards. Okay, so let's start again. So you all had excellent questions during the break. So don't be shy to ask them during the lecture. So just because I think they're interesting for everyone. So let me just maybe even just repeat a few of your questions because I think they are interesting to everyone. So one question was, for example, like, okay, wait a second, where did this 10 to minus 2 come from, right? So that 10 to minus 2 came from the observation of the CMB that the tensor to scalar ratio cannot be larger than 0.1 because we haven't seen the tensor modes. The tensor modes, right, this was the equation I was referring to that I hoped you had seen last week, and some of you had, and some of you were asleep. That was proportional to Hubble squared during inflation, right? So the bound on R is a bound on the Hubble scale of inflation. And now if I go in a most optimistic scenario and I say at the end of inflation, I take the entire energy density that is in the inflaton sector and I instantaneously convert it into radiation, then I get the maximal temperature that the universe can have had. And really the only way to avoid this is to say, well, I don't believe in inflation, right? But this is, nothing else enters here. And then the maximal temperature is about 10 to the 16 GeV. And then compared to the Planck mass, this is what gives the factor 10 to minus 2, right? And then we've also clarified, okay, why is it linear? This is linear, right? Because there's another M Planck in the Hubble rate, right? And that cancels one of the powers of M Planck, and then it goes from quadratic to linear, so this is actually correct. Then there was the question, here I took the 2-point function of the Hij, right? So why don't I get a cosine square? Why only get a cosine? Right? And the point is I get the cosine here of tau minus tau 1 times tau minus tau 2. So then I use trigonometric identity. This is the cosine of the difference. There's also the cosine of the sum, but the cosine of the sum is rapidly oscillating still with tau, right, which is my time today. And then when I do the averaging to get the energy density, that drops out. Okay, so do ask questions, right? They're all good. I was told that there's only 2 types of questions, right? Either the other people don't know the answer either, right? Maybe also not the lecturer, then it's a good question. Or everybody else knows the answer and makes them feel really smart and very happy, okay? So don't be shy, ask questions. So, where was I here? So let's go to a concrete example, the one I've been mentioning in words a few times, first order phase transitions. Okay, so what is a first order phase transition? Imagine I have some scalar potential, depends on some field phi, and at some high temperatures, phi is safely at the origin, and at some low temperatures, phi is going to be, the symmetry is going to be broken, right? Phi is going to get a VEV. And now the point with the first order phase transition is that as I go from this situation to this situation, I have to tunnel through this barrier, right? So there's no point where I can just safely roll from here to here, right? But I actually have to go through the tunneling process. And that means, right, that I kind of initially start off with my false vacuum, and then bubbles of the true vacuum start popping up inside my false vacuum, right? Like water boiling, right? Water boiling is a first order phase transition. Standard model Higgs, right, is not a first order phase transition, is a crossover, so much smoother. Why do I want something like this? I want something like this because I'm looking, that was another good question, right? Why am I writing pi and not pi ij and not tij in the source, right? So in principle, yes, this was the energy momentum tensor, but I know at the end of the day, I'm going to anyway be projecting into TT gauge. So the thing that matters is the tensor part of the energy momentum tensor, right? That will be the thing sourcing the gravitational waves. And when I mean the tensor part, I call it pi, and when I mean the whole thing, I call it t. So since we know we're going to be looking for something which is anisotropic, right? So something which is a large quadrupole moment, something which is kind of violent and not homogeneous in space, is a much better way to get gravitational waves. So this is why the first order phase transition is going to give us a signal, whereas the crossover is not going to do anything. How does it give us a signal? There's different ways. So maybe the most obvious is bubble collision, right? So if I form a single bubble, and then that bubble of the false vacuum expands, that's not going to give me gravitational waves, right? Because that's a circular symmetric situation. It will have no quadrupole moment. But if I have more than one bubble, right, and then they start expanding, and I get funny things like this, right, then I get quadrupole moments, and I get a lot of motion, I get a lot of vibration, so that would help. Then I get what is called MHD turbulence. So that is magneto-hydrodynamic turbulence. Again, right, so this is now just kind of describing the plasma sloshing around in a turbulent way, so in a nonlinear way. And then I can have sound waves, which indicate that even once kind of my bubbles have all kind of expanded and filled the space, right? Now my plasma that I have is kind of still sloshing around, and there will be some sound waves propagating through my plasma, and also those sound waves will generate gravitational waves. So we can try and estimate, and I underline estimate, right? Because doing this properly is very much an active topic of research. But let's estimate the gravitational wave amplitude that we expect from this process. Right, the frequency, we already know, right? The frequency was the estimate we did way at the beginning today. Let's try and get the amplitude. So for that, we define what we call beta, which is a time scale for the phase transition. So let beta be gamma dot over gamma, where gamma is the nucleation rate of the bubbles. Right, this means that 1 over beta is the time scale of the phase transition. Right, 1 over beta is roughly the duration of the phase transition. And then we will also define alpha. Alpha is the energy release during the phase transition, so it's basically this amount of energy, which this thing I call rho vacuum. So rho vacuum normalized to the total energy density, rho radiation. So if you have some microscopic model of a phase transition, right, I don't know, some 5 Higgs version of the standard model phase transition, you can, from your Lagrangian, right, from your microphysics, you can compute these two quantities. This is pretty simple. This is just, okay, you know the scalar potential, you get this quantity. This is more complicated, right? You need to kind of compute the nucleation rate from the true vacuum to the false vacuum. False vacuum to the true vacuum. Yes, yes, it's just that, yes. No. It's not obvious, but I have a system with the blackboards. I just keep on forgetting it. Okay, so now we take the equation I just erased, right? Fantastic. So we take the equation of motion for the gravitational wave, right? So basically, del t squared h is 16 pi gh, right? Very roughly. Well, let's put the box here. Put the box here. Okay, and now I'm going to estimate. I'm going to use the nucleation rate to estimate the box, right? To estimate the time scale. So beta squared h is 16. And now we get to the issue where I have a small pi and a big pi. Okay, so this is a small pi. This is this small pi. Right, this is 3.14. And this is a big pi. And this is the stress component of the energy momentum tensor. Okay, and now we can plug this into our formula for the energy density. So we obtain for the energy density, well, okay, we can solve this for A, and then we can solve this for H dot, right? So H dot, we just bring 1 power of beta on the other side. 16 small pi, G big pi. It's kind of all fine as long as they're not in the same equation. And now we plug this into the expression for the energy momentum, for the energy density, right, which is essentially just H dot squared. So H dot squared and the prefactor 32 pi G, small pi G. Plug this in here, 8 pi G pi squared beta squared. So now we just need to estimate what is this pi squared, right? So the energy in the phase transition. So we can expand, right? So let's call this pi divided by rho vacuum divided by rho radiation. Okay, this we know. This we know. This is alpha, and this we will call kappa. And so we plug it all together, and we get for omega gravitational wave, so the amplitude that we observe today, the rho radiation, right? This is the energy density divided by the critical energy density. So we need to take this guy, divide by the critical energy density. Maybe I should write it. So rho rad divided by rho c. Okay, so this is about 10 to minus 5. Then, but we can also write this as, this is proportional to the Hubble scale at that time. Okay, so then we combine this factor and this factor, we get h squared over beta squared, and we get kappa alpha squared. Okay, so what does this tell you? So if you have a phase transition, right, which is sufficiently fast, right? So if this is sufficiently slow, right? So if you have a phase transition where this can be order 1, okay, and sufficiently violent, right, in the sense that alpha, right, which just kind of tells you how much latent heat do I have compared to the ambient temperature. So this can also be close to order 1. And sufficiently anisotropic, right, which means that the anisotropic part of the energy momentum tensor is comparable to the isotropic part. Then you can really get an amplitude of order 10 to minus 5, which is above the BBN bound. Okay, so very violent phase transitions are in fact already constrained by CMB and BBN observations. The milder you make the phase transitions, the smaller, so all these factors are kind of strictly smaller than 1. But they can be close to 1 in part of the parameter space. And that's the part of the parameter space that, okay, if you're really at 1, you're already excluded. And if you're kind of close to 1, then it's definitely something that is testable if you have a detector at the right frequency. And the frequency, right? The frequency is roughly what we estimated earlier, right? So I said that typically, again, I mean, this is a model-dependent statement, right? But also this epsilon star parameter, where you can get with similar estimates. Right? So typically, this epsilon star is about 10 to minus 3 for phase transitions. And so the peak frequency is something like typically 10 to minus 3 hertz t over 100 GeV, right? Which means LISA can probe the electric phase transition, right? So I say again, in the standard model, the electric phase transition is a crossover, so no gravitational waves, or none in any appreciable amount. However, if you have modifications of the standard model where you make the Higgs sector more complicated, and if you arrive at a phase transition like that, which is the first order phase transition, then you can actually get really appreciable signals for gravitational waves. And hence, by performing an experiment such as LISA and probing this frequency range, you will be able to constrain extended Higgs sectors to the degree that they give you such a phase transition. And I stress again, this is very rough, right? So people spend a lot of time in trying to get, so let me draw, so roughly, right, what we get here will be omega f, right, and we get some sort of peak, right? And LISA will maybe be coming down here, right, be able to probe this. People spend a lot of time in understanding really exactly what are the slopes, right? What is this slope? What is this slope? How exactly does this peak look like? And to do that, you need to really in detail understand all these different contributions, right? Because it's not even clear which contribution is dominant. And people do detailed numerical simulations, but also build semi-analytical models, because in the end, you would want to do, you don't only want to compute this, because this is BSM, right? So you don't only want to compute it for one parameter point, which you put on a supercluster and you do the computation, but you really want to be able to scan the entire parameter space so that you can really make predictions and say, okay, this class of models has this prediction for LISA for this parameter range. So people also spend a lot of time in developing analytical or semi-analytical models to really be able to pin down these predictions so that by the time LISA flies in, I don't know, less than 10 years from now, we really have precise predictions. So that then if you measure something, or you measure, you don't measure something, but then you need to do the inverse problem and say, okay, I've seen something, or I haven't seen something, and I want to understand what does that imply for the parameter space of my model. Yes? So this is dimensionless.
Yeah, but I mean the overlap is h squared.
So beta, okay, beta is 1 over t, right? So beta has mass dimension 1, and Hubble also has mass dimension 1.
Yeah, no, but then yeah.
So this looks fine, no? This is mass dimension 1.
No, this is fine. Yeah.
Tell me where? Here? Here? Which factor? I mean, here I've just taken this pi, and I've just multiplied with 2 factors of this and 2 factors of this. Ah, no, this is a proportional too, right? There's also an Planck here. Yeah, yeah. Any other questions? Yeah. Right, so this is a pi, right? So, so I was already terrified of the 2 pi's, right? Does that answer the question? Right. So again, I mean, this is really a tilde, right? So for the, if I think of, so the dt squared, right, that is really the beta squared, right, because that's the time scale, right? Now you can ask, wait a minute, but what about the length scale, right? But, in cosmology, length and time, right, it's all the same thing, right? So because basically something happens at a certain length scale, and that automatically leads to, or something, the bubbles form at a given time scale, but that automatically kind of applies a length scale, which is kind of the same thing. Okay. Okay. So that was the two examples I wanted to give you for transient sources, right? So one, the cosmic gravitational wave background, and two, the phase transitions. Notice that they are kind of transient for different reasons, right? I mean, this is really something that happened at a given time, and the cosmic microwave background is more something that kind of, the more you cool down the universe, right, the less gravitons you'll be emitting. So though in principle this is an integral over all times, it's very highly UV dominated. And hence it's effectively something that is actually only happening for a short period of time. But at the end of the day, kind of the way they show up in the integral that we had beforehand is that they're just kind of happening. I only need to perform my integral over some short period of time compared to cosmic history. Now, the other example or the other case is continuous sources. Right, the first example of that is inflation. I won't discuss that again because we already discussed the spectrum the other time. I will maybe draw the plot of the time logic, right? Because that was also a question that came up after the talk. So what I'm drawing here is as a function of time, right? Or, yeah, time or inverse temperature. A given co-moving mode and the co-moving Hubble horizon, right? Where this thing here is inflation, right? And this thing here is post-inflation, so radiation or matter domination. So what inflation does, right, is that way over here on the left, where your modes are smaller than the horizon, right? So here you're on sub-horizon scales. You source your quantum fluctuations. Then your quantum fluctuations exit the horizon, right? Because you have this guy here decreases with time. They stay outside the horizon. They're frozen, right, as we discussed. And then, so super horizon. And then at some later time, when the Hubble horizon starts growing again, these modes re-enter, and then we can observe them today. And now the statement is that, okay, here I've just drawn it for one mode, right? But there's more than one mode, right? At some later point in time during inflation, we can have another mode. Oh, green and white is the same. Also the same, okay, whatever. So at different points in time, right, I have kind of different modes which are entering the horizon. So constantly, if I'm an observer over here, well, I'm an observer which lived before CC domination, right? But constantly kind of new modes are coming into the horizon, and hence they are building up the spectrum, starting from high frequencies and going down to low frequencies. And hence we get the spectrum that we saw for inflation, which is really a very broad spectrum, right, extending over many, many orders in magnitude in frequency. So single field slow roll inflation. Right, is this. It's very beautiful. Unfortunately, the amplitude that we get which again is constrained by the non-observation of the tangent to scalar ratio in the CMB, is so small that we're not going to see it anytime soon with gravitational wave detectors other than the CMB. Now, you can, however, complicate your model of inflation, right? And complicate may also mean make it more realistic, right? Because maybe just writing down m squared phi squared is not the end of the story. So you could have, during inflation, an additional source to the energy momentum tensor, right? So if you imagine that during inflation, you have an additional, and let me call it classical as opposed to here where you're really just exciting quantum fluctuation, an additional classical source of pi 8 ij. And one example for that happens in, if I take the inflaton to be an axion-like particle, A, and I can couple that to gauge fields. And then what happens is that during inflation, as this axion-like particle is moving, you trigger a tachyonic instability in these gauge fields. So you get a whole bunch of gauge fields. You start exponentially producing gauge fields. Now, normally, you don't care about particle production during inflation because everything is being expanded away exponentially. So who cares if there was particles? They just get diluted away. Here, since you're producing them exponentially, you do care, because despite the expansion of the universe, these guys kind of remain a significant contribution to the energy density of the universe. And they can source, significantly source this pi ij. And so they can give you a significant contribution to the gravitational wave spectrum from inflation. And now typically you want to arrange it in such a way that at CMB scales, so very large scales, where we have CMB observations which are really shouting at us, single field, slow roll inflation, nothing else, you want these effects to be negligible. And then at smaller scales, where CMB is blind, you can imagine that you get significant contribution and hence large contribution to the gravitational wave spectrum. And that's where detectors such as pulsar timing arrays, LIGO, LISA, where they are sitting. Okay? So it's only single field slow roll inflation which is impossible to see. There are other models of inflation which are not completely crazy, but also not, as simple as data-driven as the simplest version. But again, also a null observation, right, will tell you something, right? It will tell you something about the parameter space of these models at the very least. And the other thing you could do during inflation is you could construct a model which is a strong enhancement of the scalar power spectrum. So the typical way to do that is to say you have a scalar potential which at one point in time gets very, very flat. And then the scalar power spectrum, which goes as 1 over epsilon, where epsilon is the first slow roll parameter, so 1 over the velocity of the inflaton field, that blows up. And so at one given scale, you get an enhancement of the scalar power spectrum much, much, much beyond the value of 10 to the minus 9 that you measure at the CMB. So again, the idea is at the CMB, everything is single field slow roll inflation. But then as inflation proceeds, you kind of reach a very flat point of the scalar potential. Your inflaton gets stuck, and you're kind of building up scalar perturbations at this one scale. And so you can get values here which are not 10 to the minus 9, right, but maybe 10 to the minus 2. And if you get such strong scalar power spectrum, then my story of the scalar vector tensor decomposition breaks down. Okay, because I told you scalar vector tensors decouple, but that was only true in linear order. So if I really blow up my scalar spectrum that much, then I can start sourcing gravitational waves from scalar perturbations, right? So then I can have something like 2 scalar perturbations go into a gravitational wave, and I can get a gravitational wave spectrum which follows the scalar spectrum that I was generating. Okay. Again, this is not something which happens easily. It is something you have to kind of construct, right? But it is something that people look at mainly because if you play this game, not only do you get gravitational waves, but also these scalar fluctuations typically give you some abundance of primordial black holes. So typically models that give you primordial black holes, and hence a dogmatic candidate, at the same time give you gravitational wave spectrum. Again, it's not, if your goal is just to do inflation, right, you would not go to this complicated scenario, right, you would just stay here. But if your goal is to think of more complicated models of inflation, to see what inflation can do for you, to see if you can generate primordial black holes, right, then let me just mention that there's an automatic co-production of gravitational waves in these models. And okay, I can give you, is it useful? I don't know, maybe it is. I can give you here what you get for the gravitational wave spectrum. You will get, so say you have an amplitude. Okay, so this is the power spectrum, right? This is the amplitude. So say you have an amplitude of 10 to minus 2. Then that will, and you have some, okay, some shape function, but that which describes the shape of the scalar power spectrum, but is it normalized to 1 at the peak. Then what you get is here roughly factor 10 to minus 9. Okay, so if you manage to blow up your scalar power spectrum to the point where you start producing primordial black holes, which is about this threshold value, then you expect a gravitational wave amplitude of 10 to minus 9, which is, interestingly, pretty much where nanograph is seeing something. Okay, now we'll talk about nanograph tomorrow, or pulsar timing arrays, and there's easier ways, much easier ways, to explain what they see. But it is kind of interesting that the threshold for primordial black hole production kind of coincides with an amplitude here, which is definitely an amplitude that we can reach observationally. Okay, so we've already reached this with pulsar timing arrays. We will get there with LIGO, we will get there with LISA. So we will be able to kind of test these ideas. Any questions? This is the gravitational wave spectrum for this scenario, right? So the gravitational wave spectrum that I get if I enhance my scalar power spectrum to the point that I start producing gravitational waves from scalar perturbations. Yep. Not necessarily. No. You mean that makes? Not necessarily, right? I mean, you just need a very flat point in the potential, right? Okay, you're saying that if I can't do with m squared phi squared. No. Like even if I do think of a Higgs potential, right? A Higgs potential is a very flat point on the top. Right, okay, then you would spoil the CMB. But all you need is a potential with an inflection point.
No, but I was thinking, like, what kind of operator would you write down Lagrange?
This you mean?
Yeah.
No. But this is not an operator, right? This is just, we did perturbation theory, right? And when we did perturbation theory, we linearized everything, right? So we said that we can only keep linear order in the scalar perturbations and linear order in the metric perturbations. But that's only true if they are small, right? So this is simply the nonlinear theory of scalar interactions with gravity. So you get it everywhere, right? I mean, I don't know. Like, I mean, in any term in the metric, which has a g mu nu and 2 powers of the scalar. So to give you an example, this is probably not a good example, right? But del mu phi, del nu phi, g mu nu will have this. This is probably not the best example because now we have derivatives, right? But you get these terms. Another example is simply easier, right? I mean, you have the square root of g phi squared. Right, okay, so the story with the modes entering, right, is only inflation, okay? When we're talking about phase transitions or post-inflationary scenarios, right, no modes are entering, right? We just kind of relate a sourcing time to a frequency, okay? And that's what, now it's erased, right? But what we did in the first part of the lecture, where we saw that for different frequencies, we saw how the frequency is related to the temperature at a certain time in the universe, okay? So if you're asking about phase transitions, those were the relations, right? And that's where this expression came from, okay? Now, if you're talking inflation, right, then you have to play this game, right? So you have to kind of see at what point in time in the universe did which modes re-enter, right? And there, I mean, you play the same game that we did at the beginning of the lecture, but instead of parameterizing the modes by the Hubble, I mean, instead of parameterizing the Hubble horizon by temperature, you use e-folds, right? E-folds during inflation to parameterize time, and you go through the same exercise. And what you get, let me put it here, right? So we had this spectrum here, right, from inflation, roughly, right? So this turnover was the reheating temperature, right? So it depends what is your reheating temperature, right? I don't know a priori. This turnover, I mean, I think it's small, right? I mean, 10 to the minus 15 hertz or something, maybe roughly, right? So PTA is here, LISA is here, LIGO is here. Let's say like this. Yeah, roughly. I mean, again, at this point, you can shift, right? Because we don't know the reheating temperature. Yeah. But none of them probes this early phase. This is what the CMB probes here, right? CMB probes here. Okay, so last source for today, cosmic strings. Right, this is not a complete list of sources, of course, right? But, well, some very subjective view of what I think are the most interesting ones. So cosmic strings are topological defects. The easiest way to imagine them is to think of a U1 phase transition, right? So say you have something which is initially like this, and then it becomes a Mexican hat potential, right? And now we don't care if this is first order or crossover or whatever, right? We just care the final result that the symmetry is broken. And now you can imagine that now the Higgs field, right, phi, has to go from here down into the rim of the Mexican hat, right? But in different regions of space, you can imagine it goes maybe here, maybe here, maybe here, maybe here, right? So in different regions of space, you will always reach the true vacuum, but it can simply fall into different parts of the Mexican hat. Within a Hubble patch, you know, it will want to minimize gradient energy and it will kind of align itself. But beyond the Hubble patch, it's completely random. So what you will expect is kind of, if I look at one 2D slice of the universe, right, there will be a bunch of patches, each one roughly Hubble horizon. And in each of these patches, the Higgs field will point in some random direction. I don't know, like this maybe, right? Right, so this arrow indicates in which direction here is my Higgs field pointing. And now you can have, in this situation, you can have configurations like here, right, where you see that in all directions, the Higgs field is pointing away or towards this point. And so there's no infinitesimal transformation that you can do to remove this point. And if you, this is just one slice of 3D space. If you now think, try to, imagine I have another blackboard, I draw the same picture, another blackboard, and so on, right? This point will become a string coming out of the horizon, right? So if this, what I drew here, right, is some 2D plane, right, with all the patches, then this point becomes a string going through this plane. Okay, so there will be one-dimensional objects in three-dimensional space where you've restored the energy density that you had here in the unbroken phase. And there's no way you can kind of, by any local transformation, get rid of this object. Okay, so the system will always try to minimize energy, but it cannot minimize away, and of course the global minimum would be no string, but there's no small transformation that you can do to reach there, so you're stuck with this one-dimensional object with very high energy density, right? The energy density here of the false vacuum, floating around in space. And it has no end, right? It just continues forever, and it can potentially loop back on itself. So that is what we call a cosmic string, a one-dimensional topological defect. So the energy density, right? If this is V, then the energy density will be energy density per unit length of string will be V squared. And more generally, so now I did it for the example of the U1, but more generally this arises if you have any symmetry group which you break down to a subgroup. And then if the homotopy group of the quotient group is non-zero, this is what happens. Okay, so let's forget the math, right? I mean, if you have a U1, basically any time your vacuum manifold is non-trivial, you can have this sort of formation of topological defects. Okay, and now we say we have our strings, right? We will get them, roughly we expect to get them, every once in a while, right? So roughly one per Hubble volume, maybe a bit less. And now as time evolves, these networks here will evolve. So evolution of the cosmic string network. So as I said, the thing is topologically stable, so it cannot just decay away. But what it can do, it can intersect with another string, right? In which case you will get something like this. And also what it can do, it can intersect with itself, in which case you will chop off a string loop, okay? Because it's energetically better to go, because of the string tension, it's energetically better to go into this configuration where you save a bit of string length and hence you save a bit of energy. And then once you have these loops, both the loops and the long strings, they can oscillate and they can emit gravitational waves. And it's in particular the loops which will give the dominant contribution to the gravitational wave signal. So in principle, both give a contribution, but if you compute, it's the loops that give the larger contribution. There's one more interesting point about this evolution of the cosmic string network, and that is that you can show, if you look at the evolution equations governing this network, okay, so you write down the world line action, and you look at the kinetic equations that describe its evolution, you will find an attractive solution which says that the energy density in cosmic strings compared to the total energy density in the universe is approximately constant. And this is true both in radiation and matter domination. Okay, so the idea is you form this network, you have initially some equilibration time where you do this sort of gymnastics, but then you reach a steady state solution where you have a constant fraction of the energy density in the universe in cosmic strings. And this is why this is a continuous source. Okay, because once you form the network, it's stable, the energy fraction is constant, and it just forever kind of continues to emit gravitational waves through the formation of loops and the oscillation of these loops. So what does the spectrum look like? Okay, maybe I draw a big plot and we can put all the sources. So roughly the spectrum will look like this. It will, okay, let me draw it first. Give you some scales, nanohertz, millihertz, kilohertz. So you will get this plateau, which looks very much like the plateau we got from inflation. And the reason is very similar. The reason is that when these loops, they get chopped off from the string, their typical size is the horizon size. Right, so again, epsilon star is about 1, because there's no other scale in the thing, right? I mean, it's kind of, it has to be the Hubble scale. There's just no other scale in the problem. And then you basically have a source, which is order Hubble. And then the universe evolves, and you still have the source, and it's still order Hubble. So it doesn't matter if this is a string or if this is a mode entering the horizon, right? I mean, the scaling will be the same, which is why this spectrum very closely follows the spectrum from cosmic from inflation. And the only difference is that whereas the spectrum from inflation would kind of continue up here, right? This thing here decays, and the reason is that simply here you get close to present time, and you're running out of time to generate loops to make gravitational waves, right? If we had another, well, if you didn't have, yeah, if we had another gazillion billion years, right? And maybe no lambda domination, OCC domination, right? This spectrum would continue growing to the left, right? And would look more and more like inflation. The other difference to inflation is that this is much, much, much above in amplitude the spectrum that we expect from inflation. Because inflation was intrinsically vacuum fluctuations, right? Which were then enhanced and extended to give us the gravitational waves. Here we have a classical source with potentially a large energy density from this phase transition. And interestingly, this amplitude here scales, it scales with mu, so it scales with v squared, right? Meaning the earlier the phase transition, the higher the energy of the phase transition, the easier it is to see this, right? Because the string will have a higher energy density, and hence it will give us a signal which is easier to see. So this is a way how you can probe phase transitions, say gut scale phase transitions, from the top, as opposed to colliders, which will always probe this from the bottom. So let me draw some detectors, right? So let's say here we have pulsar timing arrays, right? They can already see this, right? So they already put constraints. You have LISA, which we don't have yet, but we will have soon, we hope. And you have LIGO, right? So already LIGO constrained the scenario. Pulsar timing arrays constrain the scenario. LISA will completely dig into the scenario, right? So the current bounds already push this scale to be a bit below the gut scale. Yeah, scale of grandification. Let me make two, before I draw in the other spectra, let me just make two comments. So one is, I should mention that there is a big uncertainty in the calculation of this amplitude. And this uncertainty, maybe we should discuss in a discussion session when it's not recorded, right? Let me phrase it in a neutral way. So there's two ways of basically modeling this network. One is the Nambu-Goto approximation, where you say the string is strictly one-dimensional, and you just model it as the evolution as a one-dimensional, the world line of a one-dimensional object. And the other way is to say, well, wait a minute, this came actually from a classical field theory, right? So I take an abelian Higgs model, I put it on a lattice, and I actually evolve the field theory. The advantage of the Nambu-Goto approach is much simpler, right? And hence you can evolve this over much longer times, and you can really kind of reach the scaling regime, right? And kind of really make predictions for the spectrum. The disadvantage is you've completely lost all information about the fundamental physics, right? The disadvantage, on the other hand, of the abelian Higgs model is it's much more expensive to simulate. And you have two scales. You have the width of the string, which is something to do with the microphysics scales of this potential here, and you have the string-string separation. And now you're in an expanding universe, right, where these two scales are getting separated. And so if you put it in a lattice, you're going to lose resolution, right? Either your box is too small to fit two strings, or your resolution is not good enough to actually resolve the width of the string, right? So both methods have clear advantages and clear disadvantages. Unfortunately, they disagree. They more or less agree on the shape of the spectrum. They disagree on the amplitude by, well, it depends on the value of V, right? But easily 4 orders of magnitude or more, which makes a difference if you want to see this with Lisa. So that is an open question to be solved. The other comment I will make is that here we've taken the strings to be stable, right? Which is what happens if you have this type of setup. Now, there is an addendum to that, and that is that if you take this U1 symmetry and you embed it in a full God theory, you can have a situation where you don't only have this type of topological defects, but you also have monopoles, so zero-dimensional cosmological defects. And if you have that in your quantum field theory, right, even if you don't have it in your universe, right, because you've solved the problem by inflating them away or something like that, you can potentially pair produce the monopoles along the string. So you have a method that the string is actually not topologically stable, but it can decay. It will decay with a very long lifetime, because you have an exponentially suppressed process of pair producing a heavy particle along the string, but it could decay. And in that case, you would suppress the low frequency part of the spectrum, because that's the part that is generated at late times. Right? So that would give you a scenario where you might not see it at pulsar timing arrays, but you would still see it at LIGO, right? Which is one of the reasons why it's so important to really have the different detectors at different frequencies to really, if you see a signal, that would be absolutely crucial to understand what type of a signal you actually seen. Okay, so let me wrap up by just giving you an idea of what the other signals were, right? So this was the cosmic string. One example of the cosmic string signal, right? It scales, the amplitude scales with V squared. Then a phase transition, right? I mean, it depends on your parameters, right? But say, so the BBN bound, I should mention. So LIGO is already reaching the BBN bound. So LIGO reached about 10 to minus 8, right? So this should be 10 to minus 8. So BBN bound, let's say, is here, right? So if your model lives up here, it's excluded. The phase transition, right? It will depend on the parameters of your phase transition, right? But you could easily imagine phase transition here, right? Which is at the electroweak scale and would give you a beautiful peak in Lisa. Inflation, again, we said it's super nice, but it's super hard to find, right? So inflation is, I don't know, something like this. This is inflation. I'm not sure this is the scale, right? But the point is it's hopeless, right? If you have a modified model of inflation, right, you would say, okay, you start somewhere here. Here you're constrained by CMB, right? So here you cannot do nothing. But then at smaller scales, you could try and, do something crazy or not so crazy, right? And you could get a signal that you could see up at detectors. What else did we talk about? The cosmic gravitational wave background, right, is at much higher frequencies. Also relatively low amplitudes, right? So it would be maybe over here, right, at 100 gigahertz with a Planck spectrum. This is the CGMB. And let me just say that this phase transition, I mean, it really depended on what you put for the scale of your phase transition, right? You can move this to the left and right, depending on the model you would like to look at. Okay, so I think with that, I wrap up for today, but happy to take any more questions.